Hi everybody, welcome back. Today we're starting chapter 4, which is on some applications of using the derivative. So in this chapter, we're going to be looking at more real-world applications, trying to show you how calculus can be used to optimize functions and different parts of it. Okay, so we've been learning in these other chapters a lot of rules and techniques to find the derivative. So now we're kind of going to put all that to work. So in this first section, we're going to talk about concavity and something called points of inflection. Okay, and you're going to see those come into play later on in some different sections when we're working with the real life applications. So we're going to, in this lesson, talk about the fact that the derivative function, f prime of x, is its own function, right? It gives you an equation, so it is its own function. And that means that we could find the derivative of that function. So the derivative of the derivative is called the second derivative. So we use double prime instead of f prime. So when you see f prime, that's the first derivative. Now we're going to do f double prime, which is called the second derivative. You do them the exact same way, okay? So that nothing is new. It's just the second derivative is a derivative of the first derivative. So it tells you here that the second derivative can be used to determine the concavity of a function f of x. So we're going to talk about concavity in just a minute. This in turn will help us describe and understand the behavior of a function better than just the first derivative. Remember what the first derivative did. It told us about where graphs were increasing and decreasing, and it told us about maximum and minimum values. So that was what the first derivative did. And so now we're going to talk about the second derivative and what it can do for us. Okay? So today we're going to find the second derivative. We're going to just make sure you understand what that means. And then we're going to try to find where our functions are concave up and concave down. So we're going to list those intervals. And then we're also going to look for hypercritical values of a function, okay, if they exist. And then we're going to determine points of inflection based on that. Okay, so 3 things we're going to be looking at today. Okay. All right. So at the top of the second page, here's the beginning to our concepts and definitions. We've got 2 pages of this coming up. So lots of new words for you. So keep these handy if you need them as you're working on your homework. So number 1 says the second derivative f double prime of x f double prime of x, if it exists, is the derivative of the first derivative. Okay, so that's called the second derivative. Number 2 says, in the context of motion of a particle through time, the first derivative would represent velocity, and the second derivative will represent acceleration. Okay, so that's just in context of doing motion problems. We'll talk about that. Number 3 says, a curve that is concave upward lies above the tangent. Let me say that again. I missed a word. A curve that is concave upward lies above the lines tangent to the curve. That is, the tangent lines at those points will rest below the graph of the function. All right, so concave up, just so give you an idea. Concave up is kind of like you could pour something into it like a cup and it would stay. So this would be concave up, something like this. Okay. And so what this is saying is if you pick any tangent line, here's a tangent line. If I draw the tangent line right there, it's below the curve, right? So any tangent line that you can draw and the curve is above it at that point, that part of the graph is concave up. So if I take a point over here and draw a tangent line, okay, it's still below the curve. The curve is above the tangent line. So these are concave up parts of the graph. So on the other hand of that, number 4 says a curve that is concave downward lies below the lines tangent to the curve. That is, the tangent lines at those points will rest above the graph of the function. So concave down to me, I always think of it as upside down cup. Okay? This is concave down. Okay? So if you look at these tangent lines, pick any point on the graph and draw a tangent line. The tangent line is now above the graph. Okay, so the graph is below the tangent line here. On concave up, the graph is above the tangent line. So any graph or any point on the graph where you draw a tangent line will be above the graph. So that's what number 4 says. Okay? All right. Now, I want to just take a minute and do one other thing with you about concavity because I feel like this is kind of important that you understand this to kind of put it all together. So I always like to draw this little picture here of concave up and concave down. All right. So we know that concave up looks like this. Okay, and we know that concave down looks like this, right? So if we split this up, because this is what students have a hard time understanding. If I split this up right here at this, I guess, halfway point of the cup, if you want to think of it, okay, we got two parts. We have this part, so I'm going to draw that here. And then we have this part over here, which looks like that. Okay, so both of these are concave up. So when you're looking at graphs, sometimes you're not going to see this whole thing. You might just see this part, or you might see this part. So you have to understand that these are both concave up because they're part of this curve, right? Same thing over here. If we look at the concave down curve, this right-hand side looks like that, and the left-hand side looks like that. So both of these are considered concave down. When you look at this, that makes it very simple to see that's concave up, and when you look at this, it looks like concave down. But when you're breaking them up into fourths, if you look at each piece of them, that might give you guys a little bit of trouble. Now, the reason I break that up is because that's what you're looking for on the graph, but also we got to talk about increasing and decreasing. Because remember, we're going to be putting the first and second derivatives together. And the first derivative talked about increasing and decreasing, okay? So when you look at this graph right here, and I draw it from left to right, that is decreasing. If I look at this graph and I draw it from left to right, it is decreasing. So both these parts of the graph are decreasing. One is concave up, this one is concave down, but they're both decreasing. Okay. Now, if you look at these two graphs from left to right, they're increasing. Right? They go up from left to right. This one goes up from left to right. So both parts of these are increasing parts of the graph. Concave up increasing, this is concave down increasing. So there's only 4 possible things that can go on with a function on a graph. They would look like one of these things, unless they're a perfectly straight line, but that's still increasing or decreasing. Okay, so this is a good chart just to keep handy because until you get familiar with those shapes, sometimes some of you have trouble with concavity. So just keep that in mind, okay? These are concave down, these are concave up. This is decreasing and these are increasing. So we can break them up that way, and that's kind of helpful. So keep that in the back of your mind just for future reference. I probably will reference that. All right, let's move on to number 5. Number 5 says, suppose that f of x is a function and f prime of x and f double prime of x both exist on an interval from a to b. All right, so if that's all true, then if the second derivative is greater than 0 for all x's in the interval from a to b, then we know that f is concave upward, okay, between that interval. So if the second derivative is positive, then the function is concave up. So remember, when the first derivative was positive, that meant the function was increasing, right? So now we're looking at concavity. So the same thing is true for decreasing, okay, or negative numbers. So if the second derivative is less than 0, meaning it's negative, then the function is concave down. So remember, when the first derivative was less than 0, that meant our function was decreasing. So that's why I gave you that chart just a minute ago, because now we got 2 things going on, and it gets a little confusing, but you just got to remember. It makes sense that if the second derivative is positive, positive means up. If the second derivative is negative, that means downward, right? So you can kind of remember that pretty easily. All right, number 6. Suppose that f of x is differentiable. That means we can find the derivative of it on an interval from a to b. Then if the first derivative is increasing on that interval, then the function is concave up. Okay, so be careful with that. If the first derivative is increasing, then we know the function is concave up. Okay. All right, and the same thing, if the first derivative is decreasing, then we know the function is concave down, okay, in that interval that we were given. All right, so again, lots of stuff, so don't panic yet. We're going to put it all together in a little bit. So I've got one more page of definitions to go through. All right, so now we got one other thing we didn't talk about yet, and that is the point of inflection and these hypercritical values. So that's what this page is about. So number 7 says, if the graph of a continuous function has a tangent line at a point, possibly a vertical line, it doesn't have to be, but the graph changes concavity at that point, then we call those points of inflection. All right, so if you look over here, right there, okay, that is a point of inflection because we change concavity on each side of that. On this side of the graph, over here, this is concave up, right? And on this side of the graph, this piece is concave down. So where a graph changes from concave up to concave down is called a point of inflection. Okay, so that's what that is. Now, it says those values x equals c in the domain of the function where the second derivative of c is 0, or if the second derivative at c doesn't exist, those are called hypercritical values. Okay, so just like if you remember in the first derivative, we set the first derivative equal to 0 to find those points, okay, the possible max and mins, critical values. Here, if you set the second derivative equal to 0 and find those values, those are called hypercritical values, okay? But we're going to do it the exact same way, so it's not new, it's just a different term that we use for second derivative. Now, what's important about hypercritical values is once we find those, then we have to test the values around it and see where there's a change in concavity. And where there's a change in concavity, those are your inflection points. So number 9 just says an inflection point is a specific type of hypercritical value where concavity changes. So right here, this is a hypercritical value, but because it changed from concave up to concave down, more importantly, it's called a point of inflection. Not all hypercritical values are points of inflection, okay? So that's just coming up as we go through. All right, and the very last thing on here are these are just the steps on how to find a point of inflection, and we're going to go through these together. But in order to find the points of inflection, we have to be able to have a continuous function. And then what we're going to do is find the second derivative, which means we have to find the first derivative and then the second derivative. We're going to find the hypercritical values of x. So we're going to set the second derivative equal to 0, find those values. And then just like we did on the first derivative, we're going to use the hypercritical values on a number line, and we're going to determine where the second derivative is greater than 0 and where the second derivative is less than 0. And that's going to help us figure out the intervals where we're concave up and concave down. Okay? And then when you're going to be asked to list any points of inflection, well, those are where the hypercritical values change concavity from plus to minus or minus to plus. So it's very similar to what we did for max and min. So this is a good practice for you to make sure you understand, test points and the number line and all that good kind of stuff. Okay? All right, so we're going to start today by looking at the graphs and just identifying where or what intervals the graph is concave up and where the graph is concave down, and any values of x that are inflection points. All right, so let's look at 1a. Let's talk about concave up. Concave up, remember, is where we have like a regular cup going up, and all the tangent lines would be below the curve. So from here all the way to the right, this is all concave up. So wherever I pick a point and draw a tangent line, this part of the graph would be above the tangent lines. So we are concave up from here all the way to positive infinity because that's an arrow, and this x value right here is 0. So we are concave up from 0 to infinity. Okay. Where is this graph concave down? Well, that's the upside down use. Okay. So right here, this part is concave up because right here when I draw a tangent line, it is below the graph. But on this side, if I draw a tangent line, it now becomes above the graph. So this is concave down, okay? And all of this is also concave down, right? Any tangent line would be above this part of the graph. So we are concave down from this point. Oh, I'm sorry, I went to 0. That is not true. Hopefully you're yelling at me right now, okay? I'm sorry. We are concave up from this point, okay? I just said that and I just proved that to myself. So right here, this line, this is where the tangent lines start being below. So this is concave up from 1 to infinity. Glad I caught that. Okay. This tangent line right here is above the line, so that starts the concave down part. Okay. So we are concave down from here all the way rest of the graph. Okay, so that's from 1, and then this side of the graph over here is negative infinity, since this has got an arrow. So we are concave down from negative infinity to 1. All right, so looking at my interval, at 1, I changed from concave up to concave down. Right? So that is a point of inflection because there was a change in concavity. So this point right here is a point of inflection. It is also a hypercritical value, but more importantly, that is a point of inflection. Okay? All right, part B. All right, let's look at this and look at concave up. So concave up is anywhere the tangent line is below the graph. So remember that's when you're looking at it, that's when it's, hold on a minute, that is when it's tangent line is below the graph. Sorry, barking dogs there. All right, so looking at this graph, so wherever the tangent line is below, so remember the cup looking part, okay? So any tangent line that I draw would be below the graph here, 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 right here. When I get right to here and I draw a tangent line on this one, that would be above the graph. So this is where we're changing from concave up to concave down. So we are concave up from 0.5, looks like, right here. Let's call that 0.5. Okay, so from 0.5, and that's an arrow, so the rest of this graph is concave up. So 0.5 to infinity. All right, now, look at these tangent lines. Anywhere over here on this side, the tangent line is now above the graph. The graph is below these tangent lines right here. Okay, this tangent line is horizontal. Okay, so that means that's not there. And then we've got still tangent line be above it, tangent line over here above it. So all of this is concave down. This is concave down, this is concave down. Right here we have a little blip, it's a corner, so there's no derivative here, that's going to be probably where the derivative does not exist, okay? But there's still concave down on both sides. So we need to take that point out of there. So we're concave down from negative infinity all the way to 0.5. But this point right here is a problem because it is not concave down right there. We don't know what's going on right there. So we're going to go from negative infinity to negative 6. Okay, and then we're going to go from negative 6 to that 0.5 again. Okay, so all of this is concave down. From here over, concave up. So let's talk about points of inflection. Okay, we went at 0.5, we went from concave up to concave down. So that is a point of inflection. But at negative 6, we stayed concave down on each side. So that would be a hypercritical value, but it's not a point of inflection. I haven't asked you about those yet, but that is what that would be. Okay? All right, last graph, part C. Concave up is where this graph, where the tangent lines would be below the curve, concave up. Okay, so remember my four things I gave you. That's concave up, this is concave up, right? The two parts of the cup, and then this is concave down, and this is concave down. I like to use this. This is kind of how I work the problems, but you know, however you guys want to figure that out, whether you use tangent lines or the shape. So when I'm looking at this piece of the graph right here, that is concave up because all those tangent lines are below the graph. This part of the graph, from here to here, is concave down because all those tangent lines are above the graph. And then from here on, that's all part of this cup, right? This side is concave up, and this side is concave up, right? So this graph is concave up from negative infinity over here until I get to this point, and then from this point on, right? Those are your concave up. So we're going to go from negative infinity to this point right here, negative 4. And then we're going to start again here at negative, we'll call that negative 2.5 to positive infinity. Okay? So the only part of this graph that is concave down is right here. That's not concave up. That part is concave down. So we're concave down between negative 4 and negative 2.5. That's the concave down part. All right, so let's talk about points of inflection. Okay, so when you look at these are your possible points of inflection where these numbers are. So negative 4, did we change? Yes, at negative 4, we changed from concave up to concave down. So x equals negative 4 is a point of inflection. What happened at negative 2.5? We went from concave down to concave up. So that is also a point of inflection. Okay, so this one had 2 points of inflection. Okay, so hopefully the visual is helping you kind of wrap your head around the concavity. Okay. All right. All right, so now in number 2, we're just going to start off easy, and I'm just going to ask you to find second derivatives, okay? All right, so for number 2, to find the second derivative, we'd have to find the first derivative. So we would find the first derivative of f of x, okay, which is 6x squared plus 5. That's the first derivative. So now, to find the second derivative, we would take the derivative of the derivative. So the derivative of 6x squared plus 5 would be 12x, and derivative of 5 is 0, so there's your second derivative. Okay, so you just keep going. Now that one was pretty easy because it was a polynomial. All right, let's look at 2b. Okay, this would be a chain rule, so let's see. We might have to do a little simplifying. All right, so the first derivative, let's take the derivative of the outer function. This is a chain rule, so something squared. So the derivative of that would be 2, and then we're going to leave the inside alone, to the first power, which we don't need, but that's there, and then times the derivative of the inside. Well, the derivative of the inside is 2x, right? Plus 0. We don't need the 0. Now, I don't want to leave it like this. Remember I told you, here's a good example. If you're just asked to find the first derivative, you could leave it like this. But because we need to find the second derivative, I want to simplify this. I don't want to deal with that. So let's just simplify by multiplying 2 times 2x, which is 4x, times x squared plus 7. Okay? Now, if you wanted to, you could multiply this out. Okay, let's keep going. That's 4x cubed plus 28x. Right? That is the first derivative. So for me to take the second derivative, this is much easier to take the second derivative than either one of these, right? So you do want to simplify these if you're going to use it again. So what is the second derivative now? That would be the derivative of this. So this would be 12x squared plus 28. Right? Derivative of 28x is 28. So there's your second derivative. Okay, now you don't always get to simplify it that much, but if you can, I would do it because it makes your life a lot easier. All right, now for part C, we're going to have to do a quotient rule. And so because of the quotient rule, we need to make sure that we do simplify so before we go farther. All right, so the first derivative, okay? Oh, hang on just a second. I teach this in a different class, and each time the quotient rule is given a little bit differently. And so sometimes I get those mixed up with what class I'm teaching. So I want to make sure, and I'm giving you guys the formula that you have in your notes. So give me just 1 second. Sorry about that. I always say I should write that down, but okay. So for you guys, we started with the bottom times the derivative of the top. That's what I thought, but I just want to make sure. So we're going to start with the bottom function, x squared plus 1, times the derivative of the top, which is just 3, minus, and then the top function, 3x, times the derivative of the bottom, which is 2x, all over the bottom squared. Okay? All right, so now you can see, I don't want to find the derivative of that again, because that's way too complicated. So let's simplify that a little bit. All right, so in the top, I'm going to multiply this by 3, so that's 3x squared plus 3. All right, 3 times x squared, 3 times 1. And then over here, I've got a negative, and then 3x times 2x, so that's minus 6x squared. So I can simplify that even more. I'm going to leave the bottom just the way it is. Okay, but here I have 3x squared minus 6x squared, so that's actually, I'm going to put the 3 first, so it's positive. And then 3x squared minus 6x squared is minus 3x squared. All right, so let's leave it like that. So there's our first derivative, simplified. Okay, now we could factor out a 3, but that's not going to help me find the derivative, so I think that's good. You could factor out the 3 if you wanted to. All right, so now we're ready to find the second derivative. Okay, so we're still going to do a quotient rule, but the bottom is a chain rule when we get to that. All right, so quotient rule again, we're finding the derivative of this. So we're going to start with the bottom function, x squared plus 1 squared, times the derivative of the top. Derivative of this is 0. The derivative of this term would be negative 6x. Minus, okay, the top function, 3 minus 3x squared. Now we're going to do the derivative of the bottom. Okay, and the bottom, this is a chain rule. Okay. So first we're going to do the derivative of the outside. So bring the 2 out front, make that a 1, leave the inside alone. So 2 times x squared plus 1 to the first power, which you don't have to write. And now times the derivative of the inside. So the derivative of x squared plus 1 is 2x. Okay, all over, don't forget, the bottom squared. So if we square a square, it becomes a 4, right? Okay, now, that's all I asked you to do. So you could be done there. That's fine. But I'm going to just simplify it a little bit. This would be fine. Okay, but again, if you're entering that into Hawks, that's a little confusing. So let's just combine this. So I'm going to put the negative 6x out front. Okay, that's all I did there. And then here, let's see what we can do. Let's got minus. This is, I can't break that apart or this, but I can go ahead and multiply 2 times 2x. And let's put that out front, which is 4x. And then we'll just leave the rest the way that is. Okay. All over the bottom square, or to the 4th. All right, now, some of you might say, well, can't we get rid of some of those? Yes, you could, right? You could take that away, make that a 1 and that a 3, but that's a lot that you don't have to, okay? Unless we're going to be using it, this is perfectly fine. So there's your second derivative. This would have been fine as well, okay? It's totally, the only time you have to simplify, like I said, is when you're using it. So I would do it for the top because we needed that. Here, you could have left it just like that. but I just wanted to clean it up just a little bit, okay? Not too much, but just a little bit. All right, I'm going to pause here and start a part 2 video. So you guys can either work on your homework on this first part or you can start part 2 if you'd like to now, okay?